part 2 today. So we're looking at this. This is year 2011. Okay, so we determined what's the order of this reaction. 0. How do we know that? How do you know? I'm just looking at, you don't have any of the concentration tables that were given in the previous problems. How do I know that it's 0 order based on this?
Linear.
It's linear.
Graph.
Okay, can we use like a sentence? Instead of it's linear. What's linear? The graph of,
The graph of 0 order.
well, the graph of concentration versus time is linear. If this one, if it was first order, the graph of natural log of concentration versus time is linear. If it's second order, you'd say the graph of 1 over concentration versus time is linear, indicating it's second order, indicating it's first order, indicating it's 0 order. That's your explanation. Okay? So, write the rate law. Well, if it's 0 order, its rate is equal to K times the concentration of CH3, CH2OH to the 0 power. What is anything to the 0 power? 1, right? So that means the rate equals K for a 0 order. So what are the units on K going to be? What's rate always measured in? Back over here. Rate's always changing concentration over change in time, right? Concentration's measured in moles per liter. So molarity per second, or moles per liters times seconds. Okay? That's always going to be what your rate's measured in. So the rate, the units on K, going to equal molarity per second, or moles, capital M. Now we can do moles per liter times seconds. Okay? Now, determine the rate constant. How can I determine the rate constant? I'd say that what? All right. We could use for a 0 order here. We can say A at any concentration time T. We could pick that. Okay, where do we, you can pick any one. We're going to be using this graph. I always like to, they're right there at the vertices, so it really doesn't matter which one you pick. Let's just go ahead and pick that one. So time, 1500 seconds. Concentration is going to be 0.004. So this is 0 order, so my concentration at 1500 is 0.0040 is equal to negative K times the time, 1500, and that's what unit seconds, plus my initial concentration, which is 0.01. Right? We don't have the rate, so we can't use our rate law to determine the value of K. So we have to use the integrated rate law. And what does that come out to? Anyone?
Negative 4.0 times 10 to the negative 6.
Okay, but it's going to take the negative of that. So 4 point, it's just going to be the positive. K is always positive. Anybody? Nobody trusts themselves on a calculator? This isn't exactly calculus.
It's just 4 times 10 to the negative 6.
4, well, so we'll go 4.0 times 10 to the minus 6, and it's going to be, this is all molarity divided by seconds. Molarity per second. Y'all seeing that? We have two different ways now of calculating K. We can use the differential rate law if we know the rate and all those information there, given concentration versus rate. But if it's time versus concentration, we're gonna have to use the integrated rate law to calculate. What's a graphical way we could have calculated the value of K? Get the slope of the line, right? So just concentration versus time, we could have just taken the slope, you know, rise over run, and whatever the slope is, just take the negative of that. So the rise in this one is, so K is going to equal 0.004 to 1, so 0.0060 is the rise. The run is over 1,500. That should come out to 4 times 10 to the minus 6. Okay, comes out to the same answer. So you could, that's 100% correct way to answer that question, by the way. Okay, so you can just show your slope calculation and just know that the slope is equal to the value of K.
Does that only work for zero order?
No. Okay, again, always, when this is your slope. Okay, so it works for any of them. K is always the slope. It's just negative on these two, and it's just whatever. But again, just know K is always positive. So your slope on zero and first orders are going to be negative. Slope on the second order is going to be positive. Now, y'all, we're really getting close to being finished with this. I just have talked about reaction mechanisms. And how to calculate the rate law from a reaction mechanism, what those are. That's one more day's discussion. I may get into it a little bit today. Now, turn to it was 2016. Well, actually, which one did I just run off? Which one did I just run off? I just buried it. Just made the top. Turn to 2005 for right now. 2005A. Should be the decomposition of hydrogen peroxide. And for some reason, I didn't copy the second part, the actual questions. This is the questions that go with this. We're going to be down at the very bottom. You never got a packet? Sorry. All right, 2005. Let's work through this one. I want you to go ahead. Why don't you guys just go ahead and just see what you can do? You should be able to do all of this one now. All the way to this whole problem. And the sheet I just gave to you, which is the rest of it. I'll pull this down for now and get rid of some of that glare. Feel free to ask for help. Yeah, those are .016, .017, close enough to be constant, yes. This, again, it's all experimental data, so as long as it's close, we count it. But that's a good question.
This is low battery.
Come on.
Yes.
Or is it still plugged in there?
What?
Is it plugged in?
Yeah.
Hmm?
Why do you turn on the mount but leave the bar hanging out? Don't.
If I do it on this side, the pressure closes it out on the button.
Like, you could still have it over here and just have it there. So just turn this around.
I don't know if that works. This is fine. The engineering mind, does that work? So Mark, you're finished with this? No?
Yeah.
If you don't know what to do, then you need to ask for help. Don't just sit there.
The first one? Yeah, 1 and 1. You get that? Yeah. And so rate law is K times concentration of I minus concentration of minus.
It's okay, we did extra work.
Then I just use the
It's like,
first
down the
one
slides.
to say 0.156
I did
molar
8.
per second.
It's okay.
Instead of
It's fine.
0.017 molar.
All right, let's look at this one.
0.015.
So this first part gives you concentration and rate. This is the traditional, this is where we're gonna use the differential rate law on this, okay? So we're gonna compare, we're gonna keep these two constant. So this is times what? Times 3. This is times 3. Now, without doing any work, now we're gonna show work, but without showing work, we automatically know if it's times 3 and times 3, what's the power, what's the exponent, what's the order with respect to I minus? 1. Okay, but we still have to show the work. So for I minus, we're gonna say the change in the rate. We always wanna specify which ones we're comparing. 1 to 2 is equal to the change in the concentration of the I minus raised to some power x. So 2 is equal to 2 to the x equals 1. Show work, that's what it means to show work right there. So we gotta do the same thing for the CLO. Now, again, Emmy asked the question, there's 0.17, 0.16. We can assume that's close enough for government work. Yes, sir?
Where did you get the numbers for the 2 equals 2x?
But, oh, pardon me, it's 3 equals 3x, sorry. I'm just so used to 2. but it didn't change anything. Good catch. All right, so these two are constant. Okay, so now I'm gonna look at what am I doing here, and it's gonna be times 4. So I'm gonna look at these, and it's times 4. So again, I know it's first order, but I have to show the work. I have to go through the motion. So change in rate from 1 to 3 is equal to the change in the CLO minus concentration to Y. 4 is equal to 4 to the Y. Y equals 1. So the answer to determine the order of the reaction, now don't just say X equals 1, Y equals 1, because what does the question ask?
What's the order?
What's the order? So then you have that, and then you have to say, first order for I minus. First order for CLO minus. Sometimes you say with respect to, but 4 is easier. With respect to I minus. So that you have to answer the question because it's asking for the order. You have to prove that you know that what you just found was the order. But just saying. Okay? So don't be lazy, don't be skimpy. Be complete with your answer. Always go back and make sure you're answering the question. So now, write the rate law. Well, the rate law is easy. Rate is equal to K times I minus CLO minus. 1 to 1. Then calculate the specific constant, the rate law constant. So what do I do on that?
Pick one of the.
Pick one. I always pick the first one. It doesn't matter which one you pick. It's supposed to be constant. Okay? So then we simply say, I'm going to do it right here just for simplicity's sake. The rate, 0.156, and that's moles per second, is equal to K times the concentration of I minus 0.017 molar times 0.015 molar to the first. Just solve for K. 612. Now notice that one of those molarities is going to cancel. This molarity is going to come then to the bottom, so it's going to be per molarity times seconds. Which again, you may see 612 liters per mole seconds. That's exactly the same thing. It could sometimes, because it's easier on a computer, just say liters times moles to the -1 times seconds to the -1. It's all meaning the exact same thing. Whatever floats your boat, you get to put any one of those 3. All kinds of options. Many ways to be right. Unfortunately, there are more ways to be wrong. But it's better to be right. All right, so all of this is differential rate law. They give you concentrations. Then all of a sudden, on this next part, it just switches over. And I know that it's going to switch over. How? I just heard somebody say what? Time. Because now all of a sudden I get time introduced. That means, ooh, that's going to be ding, 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 integrated rate law. Now I hate it when it's on 2 pages like this, because I can't show both pages. Okay, but we have this table, so you can refer, you have the table you can refer to on this. So now we have to answer the questions. It says the kinetics of the decomposition were studied and the analysis results show it's a first order reaction. So you need to underline that. It's a first order reaction that tells us that. So now we go over here. Oh, we go over to here. And we start answering questions. It's first order. So since that's linear, first order, what must be the y-axis?
Concentration of H2O. Yeah, I guess.
Right? Hopefully you can draw brackets better than I can. What are the units for the rate constant K? How do I do that?
Use the.
I have to use the integrated rate law, because I only have time and concentration. I don't have anything about rate. So I know I have to use this integrated rate law. Okay? So, I'm gonna go up here to B, or to 2. It's going to be the natural log of a concentration at something other than time t. So you go back to your table.
It just says unit.
Huh?
For number 2, it just asks for unit.
Oh, really? Well, let's just figure out how to calculate it anyway. If it's first order, what's the unit gonna be? It's just per minute. It's just gonna be minutes to the minus 1. Okay, but let's go ahead and calculate it. Okay, so the concentration, let's go times 10. Concentration is gonna be 0.61. Is equal to negative K times 10 minutes plus the natural log of my initial concentration of 1. So, what does that come out to?
Zero point zero
9.4? That what you got? Alright, now notice these, there are no units on these, so it's just gonna be divided by, so it's per minute. So when you have time, you have to use the integrated rate law to find the value of K, to find the concentration at any given time. So let's just say I'm gonna add in a 4. Okay? How long will it take for the concentration of H2O2 to equal 0.05 is 0.1, wasn't it? I'll start it at 1, so 0.5. What's the significance of 0.5? What's the significance of 0.5 in terms of concentration? Look at the table. Where do we start at? It's a half, okay? So in other words, we've used up half of the substance. That's what we call, the time we're looking for is the half-life. How long does it take for half of the reactants to get consumed? Okay? Now, we're looking at, so it's time is the question. So I'm gonna say the natural log of 0.5 is equal to negative a K, I already know K now, 0.0494, times time, which is I'm looking for, plus the natural log of 1. Okay, we all with me on that one? Now, when we do the subtraction, and this is where your math is going to come in again, 0.5 minus the log of 1 is equal to 0.0494 t. Right? When you subtract logarithms, that's like dividing, right? So that would be the same as the natural log of 0.5 divided by 1. correct? You guys thought you only had to do logs in math class. This is gonna equal 0.0494 times t. Well, what's the log of 0.5? Natural log of 0.5. 0.693? Yes, I always drop it off. Because this is gonna come out to negative 0.693, right? Is that what you get? Did anybody do it? All right, so what that's gonna mean is that 0.693, and then this comes out to negative 0.693, this is negative, so it's positive, divided by 0.0494 is equal to t. And we're gonna call that the half-life. Now notice, what is 0.0494? What letter do we use to represent that? K. Right? That's your constant K. The half-life is always going to be this, whatever you start with, you're gonna have half of it left. So it's always gonna be, for a first order reaction, it's always gonna be the natural log of 0.5, which is always 0.693. So the equation is really T1/2, the half-life is 0.693 divided by K. That equation is given on your equation sheet. That's the half-life equation for a first order reaction. It's also the exact same equation that you would use for half-life of radioactive decay. How long will it take for, half of uranium, to decay? So the half-life is, by definition, the amount of time it takes for 50%, half of the original material to decay, to get consumed in the reaction. And we can use the integrated rate law. We derive this equation really from the integrated rate law. But this equation is given so you can go straight to this for a first order reaction. Okay? Half-life. And here's another thing too about half-life. This is worth writing down. Half-life is only constant for first order reactions. Half-life is only constant for first order reactions. Ooh, let me see, I have a problem in my head. Am I gonna be able to find it? So look at 2014. The half-life of uncatalyzed isomerization of cis-2-butene gas to produce trans-2-butene gas, represented above, was measured under various conditions. Now, that can be very, very intimidating because what the heck? I don't have a clue as what that just meant, okay? I mean, I'm speaking from your point of view. Okay? But none of that matters. It's just a chemical reaction. It's a complicated one, and they do that on purpose to try to just overwhelm you some. But it's just a chemical reaction. Here's the initial concentrations. Now they're giving it to you in pressure, but again, remember, pressure, the greater the pressure, the more molecules that are present if they're in identical conditions. So pressure and molarity are going to be totally related to one another, directly proportional. But notice it gives the half-life here. The reaction is first order. Explain how the data in this table are consistent with a first order reaction. The only way that you know that is because the half-life is staying consistent. The half-life is not changing. It's constant temperature, we're at 350, 350, 350, so the half-life is staying the same. So only way you know that it's first order. Okay, so then we go to B. Okay, so the answer to this is it's first order because the half-life remains constant, which is only true for first order reactions. So simple answer. Now we go to B, calculate the rate constant, K, for this. Well, my first instinct is rate is equal to K times the concentration of the cis butene. I don't have concentration, I have pressure, but brackets and pressure, they don't match up. I don't really have time, I have the half-life, but I don't have time. But I have half-life. So what did we just say? T1 half is equal to first order 0.693 over K. Right? So it's really pretty straightforward question. So you just, we're set, so K is equal to 0.693 over the half-life, which is equal to 0.693 divided by the half-life, which is 100, which is going to make it 6.93 times 10 to the minus third. And the units on half-life, on K for first order is always going to be, and this is seconds, so per seconds, because this is 100 seconds.
So is the half-life for all the first order reactions, is it always gonna be consistent?
Yes, that's going to be the indication that it's first order. If it's second order, the half-life changes over time.
Zero.
Zero order, the half-life is going to just, it's going to be a linear, it's going to be a straight line, but it's going to be changing. Because it's concentration, it doesn't affect the rate. And I've never had to do anything with zero order on that. Zero order reactions are pretty rare.
When we calculate, we always have to do T1 half equals 0.693.
Yes, because I just showed you on the map, the half-life is always going to be, the top number is always going to be half of the bottom number, which means you're always going to be taking the log of 0.5 for half-life whenever you plug it in. So if you needed to calculate the half-life, you could even just put in here, if it's first order, whatever the initial concentration is, just put in half of that there. And then just solve for T. You would have to know what K is from previous information. Just solve for T and you get the half-life. But that equation always works. Because when you go put half of this and this, it's going to come out to 0.693 divided by K. Now, let's just finish this up and call it a day. Is the initial rate of the reaction in trial 1 greater than, less than, or equal to the initial rate in trial 2? Well, what's the only thing different between trial 1 and trial 2? It's double, right? What do you think that does to the rate of the reaction? Increases it, okay? So is the initial rate of reaction 1, what's it going to be? Less than that of 2, because the greater concentration, the greater pressure means the molecules will be colliding more frequently, increasing the rate of the reaction. Lastly, it says the half-life for the reaction in trial 4 is less than the half-life in trial 1. Why? In terms of activation energy. What's different between trial 1 and trial 4? The temperature increased. So in terms of activation energy, what does that mean? No, it didn't lower the activation energy. Catalyst will lower the activation energy. What does the increased temperature do?
Gives them enough
T1, I increase to T2. Now a whole lot more molecules have enough energy at the higher temperature. More molecules have enough energy to overcome EA, which causes the reaction to proceed at a faster rate. And I would draw that graph, since we've done it so many times. Catalyst moves the EA this way. Increasing temperature does not change EA, it just gives more molecules enough energy to make it over the hill, to overcome EA. Don't say over the hill, say overcome EA. All right? Now, Thursday, Friday, we're gonna do lab and practice problems, so you'll have practice problems. I'll probably split them up, I'll give them to you tomorrow, and you can work on them Wednesday, Thursday. And then Friday we'll do lab, so make a note to yourself to bring your lab manual, dress appropriately. It's supposed to be cold and rainy, so most of y'all are wearing long pants anyway. But it's an iodine clock reaction, it's a fun reaction, it's one of my favorites. So, we'll just go from there. All right, so just as far as planning, I have one more day of lecture, so Thursday, Friday is gonna be lab. Monday, Tuesday, we'll be going over the lab and finishing up the notes. I see a test. Oh man, well, we could have a welcome back on Thursday. A welcome back test. Because everybody will be here. All right, y'all have a great rest of the day.